hopefully you're understanding that just based on your definition, a piecewise function is just a function that has pieces. People, from the beginning of the chapter, we defined the term function. That has implications, right?
Right.
Like what? What's it mean if something's a function? Go ahead, Mila.
Each input has exactly one output.
Yes, every input has exactly one output. And that means that every graph should pass what? What's it called? Yeah, I hear it all the way around. Every single one of these things should pass the vertical line test because they are functions. Does everybody see that? So when we see this notation right here, that g of x right there, when we see that, we are allowed to assume that what is next to it will always pass the vertical line test, okay? So what you need to understand when you go to graph a little later on today is that that's just a way to make sure that your answer is correct. If at any point in time you graph a piecewise function and it fails the vertical line test, chances are you messed up. So I will go ahead and walk you through that. Again, the goal today is to graph and write piecewise functions. When we were talking about the homework, it became clear to me that some of you are letting go of some of your fundamentals with regard to graphing. When we graph, your mission is to get points. Points that you could then put on a t-chart and then use that t-chart to produce a graph of the function. But how do you evaluate a piecewise function if it's just in pieces? Let's take a look at example 1 to find out. What they're saying here is evaluate this function g of x, first of all, in part A, when x equals 1. What's a little bit weird to think about is that you can't just plug this x equals 1 in wherever you see an x. If we want to evaluate this function at g of 1, we have to decide which piece we should plug it into. So when I think about this, I'm like, all right, well, I got to figure out where I'm going to plug in 1. So I ask myself, thinking about the value of 1, which interval would it fall in? Is it going to fall into this first interval where 1 is less than or equal to 1? Or does it fall into this second category where we're going to graph x values that are greater than 1? What do you think, Ashley? Yeah, I have to plug it into the first one. And your first 3 problems on your homework tonight are just like this. You have to decide which equation, or expression rather, you should plug your x value into. And Ashley, just to clarify, why did you choose to plug it into the first one?
Because in the top it says x is equal to 1, and then like the bottom one it's saying x is greater.
Yep, perfect. Perfect, 1 is equal to 1, so that's why we use the first one. Nice job. Now keep in mind, I plugged 1 in, I got 1 out. That does make an ordered pair that I could plot. This graph must contain the point 1, 1. Yes?
So you're taking the first point of g, like g of whatever is one of your first points?
Yes, yes, yes. If I wanted to get another point, just pick another x value. Here they're going to have us say, hey, now let x equal 5. So this would be like a part B, you know. Same scale, just a different number. So they're asking us to think about, okay, well, evaluate this function now when x is 5. What would be the ordered pair where x is 5 in the problem? Would I plug it into the same first expression again? No. Haley, why not?
Because you already plugged something in.
Chris? Yeah, 5. Do you see it? 5 is a number. See what I'm circling up there? 5 is a number that is bigger than 1, so I have to plug it into that second piece there. That's what I'm going to go ahead and do. So if I want to find g of 5 this time, I actually have to plug it into the second expression in my piecewise function. So I have 15 plus 1, which is 16. So this graph also contains the point 15, 6, or I'm sorry, almost misspoke there, 5, 16. So that is how you evaluate a piecewise function. And the nice thing about being able to evaluate is that you could graph it, right? You could just find some points and produce a graph. So let's do it. Now, it does get a little monotonous to graph every single point on a t-chart. And we could all make a t-chart for this piecewise function here, but I'm going to show you another way to kind of get around that. it still does involve, to a certain extent, evaluating a function for the given values of x. So here in example 2, I'm going to let you know I'm going to color code this. This first piece here, you don't have to color code it. I'm just so that we all know what I'm talking about. I'm going to do this first piece here in red. I'm going to do the second piece of the piecewise function in red. The first one's in blue. The second one's in red. Hi, colors, Mrs. Lucas. So let's go with some basics myself here. And then that third piece, I'm going to graph in black. So there's 3 pieces to my piecewise function. So there'll be 3 pieces to my graph. For this. Okay. So back to example 2 here. The first one I'm going to graph is y equals -3/2 x minus 1. Step 1, I graph the entire function. Step 2, I erases the pieces that I don't need anymore. And step 3, I check it by looking at some endpoints. So step 1, I have to graph that function. Y equals -3/2 x minus 1. And I do that by going down 1 and putting a dot. And then I'm going to go down 3/2, down 3/2, and repeat the pattern in reverse, up 3/2, up 3/2, to get a nice line. So you plot the y-intercept, count off your slope. Fun fact, I graphed too many points. Remember that 3 days we spent on domain? All these are ever here, after this if statement, is a domain. What we're saying is I only need this line for x values that are less than -2. So up from -infinity to -2 is the domain of that piece right there. So as you can see right now, I have way too many pieces. My x value of -2 is right there, right? So I can get rid of all this business that's beyond -2. And then because it says strictly less than -2, I'm actually going to swap out that ordered pair right there for an open circle. Today's a weird day. You have to understand what you're erasing. And if you don't understand what you're erasing, don't erase. It's a weird take on the rules for notes. What's up, Ashley?
So it's anything that's like, because I thought at first it was on the y. So it's anything that's past -2 on the x-axis.
Yeah.
Okay.
Some students, the trick they use is they like build up like little walls. Like they'll put in, I'll see them put in little dashed lines. And that's the boundary that they have to graph around. So that's where x is -2. And we needed the piece of the line that was to the left of that, because we're talking about less than that. Okay, step 1, I graph the line. Oh, Mila, sorry, didn't see your hand up over there.
So if, like, when it says, like, less than -2, we would erase everything from -2 and on, like,
Yeah.
everything after -2.
Yeah, you got it. Okay, step 1, I graph the line. Step 2, I interpret the domain to erase the pieces I don't need. Step 3, I'm going to check it to make sure I have the right starting point. So here's me checking to make sure that my starting point is correct. So right now I'm checking to make sure my starting point, I don't know if you can see it there, is that open circle right there. That ordered pair is -2, 2. So I'm just going to check real quick to make sure that -2, 2 is where this graph should actually be. And I do that super easy. I just do this by evaluating my function at -2. And I'm going to make sure that I get 2 back out. So I plug in my x value and I just check to make sure I get the corresponding y value. My 2's cross cancel. And I get 3 minus 1 out of that, hey, which is 2. So I put -2 in, I got 2 back out. That means that starting point is correct for that graph. That's where my graph should start. 3 steps. Graph the equation, erase what you don't need by looking at the domain, and then I always check my endpoints to make sure that's right. You don't have to show your check, I just usually recommend that you do it. All right, let's do it again. This time we're going to do it with the red piece. I start by just graphing the whole equation x plus 1. So that's going to have a y-intercept at 1. And the slope of that line is up 1 over 1, up 1 over 1, up 1 over 1. So I graph the whole line. And then I look at the domain, and if I read that domain right there, you see it? It's basically telling me I only need this line for x values between -2 and +1. So right there. So if I'm building another wall, like Ashley and I were talking about, I only need x values in between those two green lines. So my red graph should only be between those two green lines. Because, again, it says the domain for that piece is just between -2 and 1. So now I can go ahead and erase what I don't need. So I don't need this piece down here. And I don't need this piece up here. So I'm going to take a second. These are supposed to be closed circles because these are less than or equal to. And I'm going to go ahead and check those points super quick. So I'm going to check my endpoints. My first endpoint to the left there is the point, looks like -2, -1. So I'm going to check to make sure that that actually works in my equation. So I'm going to do -2 plus 1. Hey, look at that. That is -1. So that is the correct left endpoint. And then the other endpoint that I see is just right there. And that is the point 1, 2. So I'm going to check to make sure that 1, 2 satisfies that expression as well. So here's me checking 1, 2. So x plus 1 is going to be 1 plus 1, which is 2. So I put 1 in, I got 2 out. So that point, it works in my, sorry, a lot of smiley faces there, I'm very happy today. That point actually should be on my graph. So I have the correct endpoints. All right, one more. That y equals 3. Y equals 3, that's that Hoy-Vux, H-O-Y. So equations of the form y equals a number need to be horizontal, right? So y equals 3, right there, I'm just going to draw that whole thing. So that's the line y equals 3. But I'm only supposed to have this y value of 3 as long as x is bigger than 1. So there's a significant chunk I do not need there. I basically now have to erase anything that's less than or equal to 1. So I'm going to do that. A little bit more. And then I'm going to have an open circle. Right. Open circle. There we go. And then I would check that endpoint. So I'm going to check that point 1, 3. And there's nothing really to even plug in there. When x is 1, y should be 3. It should be an open circle because it says greater than. Strictly greater than. So that thing right there should just be a good point. So that works. I'm smiley. Ta-da! Piecewise function. So you graph the equation, you erase the pieces that you don't need based on the domain that's given for that chunk, and then I always check the endpoint and make sure I started in the right spot. Any questions about that process? You have a couple of those to try tonight. We do practice this a little more tomorrow in class. Tomorrow's our review day. I'd like to read ahead a little bit. Our graphs are going to look something like that, just a little bit. Let's go backwards. I'm going to color code this again. I'm going to call this piece number 1. I'll call this piece number 2. I'll call this guy piece number 3. I'm trying to write a piecewise function that has 3 pieces to it. So here's how you set this up. I'm going to have 3 pieces. So I have my f of x equals, big J Leno bracket there. I'm going to do the first piece that's red. I'll write the equation for that. Then I write the word if and the domain for that piece. And then I'll have an equation for the blue piece, and then its domain. And then I'll have an equation for the black piece, and then its domain. So for the red piece, that's a horizontal line again, right? That's that Piecewise. So if I have a horizontal line, I need to write an equation y equals a number, and that is y equals 3. So that just gets a 3 right there. And I notice that it starts at an x value of -3 and stops at 0. So we say x is between -3 and 0, not including 0 because that's an open circle. All right, time for the blue piece. The blue piece, when I look at it right there, that it's a horizontal line again, so it has to be a constant. It's that Piecewise, right? So we have y equals, it looks like it's hitting at 2 on the y-axis. So that's going to be the line y equals 2. And then when I look at the domain, I see it's starting at an x value of 0 and stopping at an x value of, that looks like 2 there, right? Oops, need a pen. So the domain of that piece includes 0, but doesn't include 2. So x is between 0 and 2 for that blue piece. And then last but not least, I can count the rise over run for this guy. It's a line. Looks like I'm going up 1 over 1. So I have y equals 1x. And then if I just repeat the pattern in reverse to figure out where this thing's going to run in, it's going to run in at 1. So that's just the equation x plus 1. You know, do whatever you need to do there to write your equation of your line. I just repeated the pattern in reverse until I hit the y-intercept. That portion exists for when we're between 2 on the x-axis and it looks like 6 on the x-axis, right? So we would say that is for when x is between 2 and 6. You guys all right with that? Yes.
So you wouldn't do betweens unless there's an arrow?
You wouldn't do
I think I
betweens.
asked that. You only do betweens when there isn't an arrow.
Right. Yes.
There we go.
Now I'm good. So that's a great question. Let's talk about that. That's legit. Okay. So let's say what Darby's talking about is like what would happen if I put an arrow on the end of that? This then changes. How would it change? Christino?
-2 plus
2 to positive infinity, yeah. Or we would just say, you know, x is greater than or equal to 2 there. That's what that would be. Does that make sense? So if it keeps going, you can't close that side of the box. It has to, you know, we would just say it's bigger than. This is the only time we kind of use that set notation or that inequality type business, you know, if you're wondering. But yeah, that's what this answer would look like, as is. Any other questions? Go ahead, Chris. Why did I do x plus 1? Do you see why it's 1x? Because my slope was 1. You're okay with that? And then to get the y-intercept, I was just predicting in my head, you know, where would this fall on the y-axis? And that's a b value of 1 right there. You okay with that? Yeah. So I just did what I did in the first half of the chapter. I wrote the equation of the line. Anything else? Good question. Because now you guys get to try. Woohoo! You get 2 of them while I finish checking homework. Those 2 are all yours. And I'll show you the answers in a couple seconds. Spoiler alert for the second one. There's 2 right answers. 2 different ways you could write 2 different piecewise functions. Okay. There they are, you crazy kids. All right, so your independent practice. The first one actually has a name. You'll study this function a little bit more when you get into trig pre-calc next year. Some books call it a step function. Other books call it the greatest integer function. It's not in our curriculum anymore, but you will take a look at it a little more next year. We just examine it as a piecewise function, and notice those were all horizontal lines. The first horizontal line was at y equals 1, so that's how I got that. The second horizontal line was at y equals 2, so that's how we get this piece. And then the third horizontal line was at y equals 3. And just keep an eye on your inequality symbols. Make sure where there's open circles you have strictly less than. Okay, you do have 2 options for number 2. I saw this guy here as a V-shaped graph to begin with, so I wrote it as an absolute value function. You didn't have to. As you can see here, some of my students also earlier today thought about this being the line y equals negative x. It was a dance move, right? So this is y equals negative x, this is y equals positive x. And then you have to have y equals 3. So if you were worried about what it would look like, you did it the other way. It's still fine, you just have 3 pieces instead of 2. So one of yours was at negative x, one of them was at positive x, the other one was at 3. And then it's negative x for x values that are less than 0. It's positive x as long as x is between 0 and 2. And then if your value's bigger than 2, it was at y equals 3. So that would be the other right answer. So you could have one of 2 things. All right, you just have a couple for homework tonight. We'll see you tomorrow.
I'm not gonna be